Hello, welcome back to Computer Vision Zero to Hero series. Today we are going to write our first code. We will be using PyTorch to train a model, a dense neural network, a simple one to classify handwritten digits in the MNIST dataset. So this is pretty much the same tutorial from the PyTorch quick start with some extra explanations. First of all, we can take a quick look at data at the Hugging Face site. So here is the MNIST dataset. It contains quite low resolution images of handwritten digits in grayscale, so no color, and there are roughly 60K rows in the training dataset. I'm writing code on a local Jupyter notebook on an Mac M1. The only dependencies to run this is Torch and Torch Vision, which we can install using just pip, and that's it. So it should be pretty easy to set up in any Jupyter notebook on your computer, on a remote VM, on Google Colab. So PyTorch is actually quite good in that, as compared to TensorFlow, for example, which is pretty hard to make it work on Mac, for example. So let's go ahead and run it. So I should already have it installed, so it should be pretty quick. So we make sure everything is installed, we do some imports, and then we get the actual data. I'm not going to dive into what is happening here because it's like we were not the ones to write the code to fetch this data. It is provided by the Torch Vision library. We're just going to copy it as is. And let's just type what is it that we have loaded. So the type of training data is actually Torch Vision datasets, which is something I've not seen before, to be honest. Right, but then to use it in the actual training, we turn it into a data loader like that. And data loader is like an iterable API that can be used for training purposes. Right now, the setup is pretty simple for us because we actually have all the data locally. So this command sort of downloads it from the internet, saves it to disk, and then loads into memory. Sometimes it's not as simple as that. You might have data that does not fit in memory altogether, so you have it spread out into different files that you have to sort of load on the fly. Sometimes you might want to do distributed training where the same code will be executed by different nodes and every node must read their own portion of the data, for example. So data loader is sort of an API that lets you do all of that, but for now it's quite simple. And again, it works as iterable, so you can actually iterate over this data loader to load the actual data. So the shape and the data looks like a pair of features and labels. So the label looks just like a tensor of integers where every integer corresponds to a certain class. For MNIST dataset, the actual index in this, the actual integer in this tensor is exactly the digit we are looking for, right? So index number, integer 7 actually corresponds to number 7. This will almost never be the case. So for example, fashion MNIST, that is about classifying pieces of clothing, it will also have labels as just numbers from 0 to 9. But obviously the classes themselves are different. And then X is the features, and the features correspond to the actual pixels of the image, right? So the size of X is 64 to 1 to 28 to 28. So 64 is our batch size, so we basically iterate over batches of 64 images at a time. It's a grayscale image, so we only have one color to speak of. and the resolution of the image is 28 to 28. So it's quite hard to see what is going on here. So let's actually go ahead and convert it a little bit. First, let's load the first image, right? So, and let's print its shape. We can also call the squeeze method on that to get rid of this extra one dimension, right? And now let me just print it out in a better format. So instead of end of the line, I'm going to print them using just space as a separator. So here it still prints out this tensor. So I need to print out the value of the tensor. Okay. Like this. Right. Sorry. Okay, now that's better, but it's still quite hard to understand what's going on here. So let's do some formatting. Like this. This should work. Sorry, forgot how to do proper formatting in Python. Okay. Like this. Right, so this is slightly better. We can already see that yeah, we are looking at the first element, and the label for that one was 7. So it is possible to see the actual 7 somewhere in here. So let's go a bit further and try to just print out 1 if there is something in there and 0 otherwise. I just print out pixel. Right, so now it's a bit clearer, and yeah, you can definitely see a number 7 like that. I'm doing this just to show that, you know, it's not magic. We are looking the actual numbers corresponding to the image, to the level of blackness in the grayscale image. And this is exactly what we'll be passing on to the neural network. And this is how you can actually just plot it using matplotlib. And that is how it looks like. Right, so it is a number 7. Right, next we have to deal with devices. Again, for a simple neural network that probably doesn't matter, but normally you would want to use GPU if it is available. So Intel AMD-based computers use CUDA, that's an NVIDIA library for running calculations on GPU. Then Mac, at least newer Macs, use a library called Metal Performance Shaders, or MPS, which is also easy to set up in PyTorch. And then if neither of these is available, we just use CPU. And again, the only setup that I actually did on this Mac was just installing Torch and Torch Vision, and out of the box, it is the MPS device is available. Right, next we actually define our neural network. So we do that by subclassing the Torch and then module class, which basically lets us do stuff like setting the training for the model, which is to say that, you know, now start calculating gradients and updating parameters, to save the model, and so on. And we can actually print what is going on here to take a look at our model later on. So we define two functions. The init sort of sets up the layers, and that's done during the network construction time. And then forward is used when we actually call the model to get the prediction, right? So we can actually just do it like this. We can convert our first image and then place it on the device. So since we are using MPS device, we need to make sure that everything we use in a certain calculation is placed on the same device. And then we can just try to do this, right? And it worked. So we see that the model prediction works, that this is on MPS device. This is like the first test of correctness that we do, right? If the architecture is defined properly, you'd at least be able to call the model and get the actual prediction out. So, but this actually is quite simple, but still I want to go a little bit deeper and try to show that you can actually print out all the intermediate steps as well, right? So for example, this nn.linear, this is a dense layer that, yeah, let's print out the help for that. So it receives the number of input features that it gets in without the batch dimensions, number of output features or intermediate neurons or embeddings that goes out, right? So we actually start with flatten, right? So our one feature looked like 28 times 28 picture. But before we can pass that on to the dense network, we need to actually flatten that. And we do that, we can actually repeat that right here. So we can call an end.flatten to construct the layer, and then immediately call that layer on our picture, right? So we started with something with batch size, which is 1 in this case. I just took one image, times color, times 28 times 28. And then we flattened it down to just 784, right? To pass that to our first linear block, right? And let's save that to P1. Then we can actually check what happens after the first linear layer, right? And it's easy to think of linear layers as just projectors from some input size to output size. So input size is 28 times 28. And then we just decided that our intermediate representation will have a size of 512. So I should be able to see that if I just call the same layer. So again, I construct it using one call and then just immediately call it on P1. Right. Okay, now I just need to make sure that it is also on the device. Okay. It's not being allocated. Yeah, this is the sort of error that you might get if you misplaced your tensors or layers somehow, right? So I placed X to device. Flatten is just a function, it does not care. But then the linear layer has the actual parameters allocated somewhere, so I have to place it to the same device before being able to call it. And so I see that the P1 has a shape of 1, which is batch size times 784. And then I project that down to 512. And I can obviously just print the actual content as well, which is just arbitrary numbers right now because it was initialized randomly. So this is what happens in the network. So first we get original image 28 times 28. We project that to 512, then to 512 again, and then project it down to 10. And we need 10 predictions here because we are doing multi-label classification. We will be using cross-entropy later. So this basically corresponds to logits that can be converted to probability prediction for each of these 10 classes. And it's good that we can just sort of go through all of that, print that out, and see how our layers work on an example image, which is really important once the models start to become complex. Because if you just misplace one number here, it will not work, right? So the model got constructed, but you actually try to call it, you'll get an error which is quite long and a bit daunting. So it's good to be able to sort of debug it line by line. Right. Now we can delete that. We don't need it anymore. Another thing I wanted to talk about is the parameter initialization. So here we just use the default, right? We are not specifying any initialization, and we can iterate over layers like this. Let's print it. Actually, let's just break and see how it looks like. Okay, maybe like this. Yeah. So the parameters method of the model lets you iterate over all the layers defined on the model, and it actually returns the parameters associated with this layer, right? So let's just print layer.shape and see what happens. So I've defined just 3 layers, but I see 6 here. So this one, this smaller one, corresponds to biases, and the big one corresponds to the actual weights, the kernel matrix of the dense layer. So let's make sure that layer variable is just the first layer, right? This is it. Another interesting thing is that they are, although they are random, they are quite small, right? So this is like 0.03 if you convert that. Actually, let's explicitly convert that, right? I did that before. Let me find it. No. Okay. Okay, got it again. And I need to call .item to get the actual prediction out. Yeah, so it is like 0.02, 0.03. So it is not 0, obviously, because if you would just initialize everything with zeros, your network will get stuck in this sort of local maximum where it wouldn't be able to move anywhere because all the predictions are 0 and then you're sort of stuck in one place. And it's also not like from 0 to 1 or -1 to 1, right? So this actually corresponds to square root of the layer size, right? So we can check it out. So square root of 512 is roughly 22. So 1 divided by square root. So if we just look at torch and then linear definition in PyTorch, it initializes the parameters in minus square root of 1 divided by input features to plus square root of 1 divided by input features. So, sorry, we actually needed to put input features in here, right? And this is done intentionally. This is only one of the ways to do it. There are others as well, which we'll discuss later. But basically, if you just say that, let's generate weights randomly in -1 to 1 interval, what that will lead to is that since the actual linear layer is basically matrix multiplication of the input vector with this matrix, right? So the actual cell of one element in the output will be produced by multiplying this first row of the matrix with the vector of the image, and which is basically a sum of these much elements, right? And so if you get initial parameters in -1 to 1 interval, what you get is the more layers you stack on top of each other, the greater the variance of the overall prediction. And most likely the network will just go mad. It will output some crazy numbers like +1,000, +10,000. And the bigger the network, the bigger the effect, right? So by stacking more and more layers, your final prediction will be even more off. It will be insanely big, and at that point you definitely have problems. So initializing it like that fixes this problem. So you get, you can actually stack layers, and the actual prediction will be relatively small as well. So it is not vanishing down to the 0. It is not going all the way up to infinity. It is more or less from 0 to 1, hopefully. And this is actually an important part. So we'll talk about this later, but for now, just this square root of in features initialization is good enough, and this is the default in PyTorch. So let's move forward. Right, so we have checked that our model works. Now we can define the loss. So for binary or multi-label classification, we just use cross-entropy loss. Then we define an optimizer, which is stochastic gradient descent. And then we define the training loop. So again, PyTorch actually lets you define your own training loops, and it looks pretty simple. So we iterate over the examples in our data loader. Again, we make sure that we place everything on the same device. Then we compute the prediction, similar to how we did it before. Thanks to the fact that we call this .train method of the model, we sort of switched it into the training mode, which is when, apart from just calculating predictions, we also calculate gradients, or at least stuff that is required to calculate gradients. So the actual gradient is computed here. So we calculate our loss. Actually, let's take a look at that loss as well. Loss from model from X. Loss n, sorry. And we need the target. Okay. It also needs a batch dimension. And it needs the device. Right, so yeah, this is another check that we do, which basically means that the output of the model, which looked like this, it's a so output looks like 10 numbers, so it's like actually batch times 10, right? And then we just call loss of n to make sure that, you know, this output format is acceptable by our loss, and it is, so we get scalar loss. Then we do the same on every train iteration. So for every batch, we calculate loss. And then we can call loss.backward to actually compute the gradients, right? So we say that we want the gradient in respect to this scalar loss. Since the optimizer was already connected to the parameters of the network, I can now say that let's perform one optimizer step. So one step of stochastic gradient descent, and then don't forget to call zeroGrad to set all the gradients to 0. And then once in a while, I'm going to print the actual loss and on the training dataset. Then apart from training dataset, I also want to print out the loss and the accuracy on the test dataset. So this is the code to do that. Again, I'm not using any specific functions. I'm pretty much just computing accuracy myself here. And this is how we can actually train the model. So we have, let's do this for 5 epochs. So one epoch will correspond to one call to the train function, which is iterating over the train dataset entirely. So one look at the entire data. And then after one epoch, I will also print out the past error. And as we can see, it actually trains pretty fast. So all of that took only 25 seconds. And accuracy is more or less okay, I guess, right? So before we move on, I also want to train it a little bit more. Let's train it for 100 more iterations. Sorry, 100 in total, so 95 more. Just to see that it actually gets to proper numbers. So we started here with the accuracy of 25. That was already after, oh yeah, actually I did print out the accuracy before the training. So when the model was actually randomly initialized, the accuracy was roughly 10%, which corresponds to, probability of guessing the number. And now we can see that it quickly raises up to 86. Let's wait a little bit more. Okay, and it is done. So we have trained for 100 epochs in total. We can briefly see that the accuracy on the test keeps improving. So it's 92, 93, 93.7, 94, 94.1. So in the end, even after 100 epochs, we get 94.1 accuracy. This is pretty fair. We can check that indeed, at least in our case, for the number 7, it does predict correctly. So we can see that, let's look at what we started with. So it was just basically random predictions. And if we look for max in here, it was 0, 1, 2, 3, 4. Yeah, so max was on 4 and the loss function was 2.29. Now it is 0, 1, 2, 3, 4, 5, 6, 7. So it correctly predicts that it's 7, and it's quite far from all other predictions. And the actual loss function on this one test example is quite small as well. So yeah, this is pretty decent considering that it was just a simple model, just dense layers, no convolutions or transformers or anything like that. It already worked pretty well. Another important thing to note here is just how we did the training. Although this is quite a crude way of doing that, but still we did all the important stuff, right? So we keep track of loss on the training data, on the test data. We can see that despite training for 100 epochs, it did not overfit. So the test accuracy just keeps going up. So we can actually try and train it further for 1,000 or 10,000 iterations. We will not do that because we are not that interested in this simple model, but still it's worth trying to train it at least until overfitting starts to happen. So this network is basically undertrained because it just keeps improving. And this is pretty much it. So to sum up, we just trained a simple neural network with just a couple of layers on MNIST dataset. We've taken a look at how we can actually look at the input tensors, at the intermediate model outputs, at what is happening with every layer, like flatten and linear and so on, and the loss itself, which is helpful once we start debugging harder models. So thank you again for coming, and see you next time.